In 6.4, we're going to start talking about special types of parallelograms, rhombuses, rectangles, and squares. And the definition of a rhombus is going to have if and only if in it. So a rhombus has a figure is a rhombus if and only, or a parallelogram is a rhombus if and only if it has four congruent sides. So it has to be a quadrilateral, and it needs to have four congruent sides. Or it's a rectangle if it has four right angles, and if it's both a rhombus and a rectangle, then we call it a square. It's got four right angles and four congruent sides. So, one thing that people get confused on is, in order for something to be a square, it just needs four right angles and four congruent sides. For it to be a rectangle, it just needs four right angles. So every square is a rectangle, and by the definition back here, okay, go back a page. So if it has four right angles and four congruent sides, well, it still has four right angles. So any square is always a rectangle. Any square is also a rhombus. Now, a rhombus can sometimes be a square. We'll try to work this out here. Decide whether a statement is always, sometimes, or never true. A rectangle is a square. A rectangle could be a square if the sides were all congruent, but that is not a given. So that is a sometimes. A square is a rectangle. Well, a square, does it always have four right angles? Yes, it does. So a square is always a rectangle. A square is just the most specific name to give that particular rectangle. Is a parallelogram. A parallelogram is a square. So in that case, not all parallelograms are squares. We could draw some examples. Okay, that's obviously not a square. But if you drew a square, could that be a parallelogram? Are my opposite sides congruent? And so therefore your answer is sometimes. A rhombus is a parallelogram. A rhombus has to be a parallelogram, but a rhombus is a more specific name. So, knowing that a rhombus is a parallelogram, we can know quite a bit about the sides. We know all sides are congruent, okay, because of it being a rhombus. What else do we know? Because it's a parallelogram, our opposite angles are congruent, and we know consecutive angles are not congruent but supplementary. Okay, we know the diagonals bisect each other. Okay, so this is pretty much all because it's a parallelogram. Suppose since it's a parallelogram that our opposite sides are also parallel. Okay, you know quite a bit. And now we're going to a couple new things. One about the diagonals. The diagonals in a quadrilateral are perpendicular, excuse me, in a rhombus are perpendicular. Okay, so if the diagonals are perpendicular, then it is a rhombus, given that it's a parallelogram. It works both ways, remember, if and only if. Also, we know a parallelogram is a rhombus if and only if each diagonal bisects a pair of opposite angles. So it bisects these angles. And the last one's about a rectangle. A parallelogram is a rectangle if and only if, remember it works both ways, the diagonals are congruent. Okay, so if the diagonals are congruent, this diagonal has to be the same length as that diagonal. But we know the diagonals of a parallelogram bisect each other, so they end up, these pieces are also all congruent, but the total length is also congruent. That's what the theorem is referring to. And here's kind of a challenging problem. We want to solve for x, y, and z, and not given a whole lot of information to go off of. But if you remember that last picture, we talked about how all these diagonals have to be congruent. So we can start by writing an equation where we say 2y plus 3 equals 5y minus 6. This diagonal, this part of the diagonal has to equal that part. Subtract 2y from both sides and add 6. Divide by 3. We get y is 3. And how can we use that to find x? Well, we want to figure out what this is then. So put 3 in for y. 2 times 3 is 6 plus 3. This length is 9. So this length has to be 9. So x must equal 3. 3 times 3 should be 9. Now, to find z, we're going to use the fact of this right angle here. And we're going to say a squared plus z squared equals c squared. So 15 squared plus z squared equals c squared. And that's 9 plus 9, or 18 squared. So 225 plus z squared equals 324. Okay, so I subtract 225 from both sides. If this was 325, I'd be left with 100, but it's a little short, so I'm just guessing 99. So z is going to equal square root of 99, which could be simplified down 9 times 11, so 3 times the square root of 11. Now, one thing that I've used one of these theorems before in real life was when I was framing houses, we'd have to build walls, and we wanted to make sure we built walls that were square, or rectangles I should say, but right angled. And before we put them up and put plywood on the side, we'd want to make sure we straightened them out. So we would take a tape measure and measure from one corner, and somebody else would take their tape measure and measure from the other corner, and we'd make sure that those lengths were the same. We wouldn't want to measure here and have one of these tape measures say 100 inches and measure here, and the other one be at 90. That's not a square, I should say a squared up wall. It's not a rectangle. We'd want to balance these things out until we got the same number. You'd want 95 and 95. So we'd push the top over until this diagonal got shorter and matched the length of this diagonal. Here's another coordinate proof. I'm not going to do it nearly as in depth as the first one in the last section, but how to prove something is a rhombus, rectangle, or square takes a little bit more work. And we're going to use theorems to justify this. So first off, if it's going to be a rhombus, we can show that all the sides are the same length. But showing all the sides are the same length doesn't necessarily show that it's not a square. We want to use the most specific one as possible. So I am going to start with just kind of the easiest approach here, and I'm going to use the distance formula, and it looks like this side length, this is 2, this is 4, so the length of SR, is going to equal 2 squared plus 4 squared, which is 20, 4 plus 16, square root, right? And doing the same thing here, RQ is going to be 2 squared plus 4 squared, or the square root of 20. And continuing on, QP is the square root of 20, and SP is the square root of 20. So we showed all the sides are the same length, which shows that it is a rhombus, but is this thing a square? So how can I show if this is a right angle? Okay, so one thing I can do is I can look at the slopes. The slope of RQ equals rise over run, so -2 over 4, or -1/2, and the slope of PQ up 4 over 2, the slope of 2. Since these are opposite reciprocals, we know that RQ is perpendicular to PQ. Those are perpendicular lines when they have opposite reciprocals. When the slopes are the same, they are parallel. So since they're perpendicular, that's a right angle, and we already know this is a parallelogram, so if this is a right angle, this is a right angle, this is going to be supplementary, so 90 plus 90. These are all 4 right angles. The sides are all the same length, so we have a square. There's your homework. You will need some graph paper here to plot these things out again. You'll get that in class. See you then.